We shall discuss today what we mean by divergence of a vector. The symbol of divergence is, this is the grad symbol, grad operator or nabla operator is denoted by this symbol. If we put a dot after this, then we mean a different operation, and this operation is called divergence operation. Divergence operates upon a vector. Suppose the vector we denote by vector f. So this is how we denote the operation called divergence, and we call it div or divergence of vector f. Now, what does this actually stand for? We will discuss that now. Before going into anything, it is very evident from the name what it stands for. The name is divergence, means spreading out. So, in a region where a vector is defined, divergence of that vector will give us information regarding how or how much the vector is spread out in that region of space. Let us come to the formal definition of divergence of a vector, which is represented by this symbol. So, definition of divergence. Let us consider a region of vector f field. So consider a region of space where a vector f is defined at each and every point. So this is a region of f field, and in that region let us consider a point P at which we will evaluate what we call divergence of vector f. So consider a point P in this region. Now surround P, or rather include P in a small volume, say delta V, bounded by a surface, say S. So what we have done is, we have considered a small volume delta V, the bounding surface of which is S, and this small volume contains the point P. So delta V is a small volume surrounding or containing the point P, and S is the bounding surface of delta V. Let us consider a surface element on S and say this is the surface element. The outward normal is, say, n cap, and since this is a region at each and every point of which a vector f is defined, so there will be a value of vector f at the location of this surface element also, and let it be, say, in this direction. So let us write these things. ds is a surface element or an elemental surface of S, and n cap is a outward unit normal to ds, and vector f is the value of the field at ds. So let me state once again what we have done, and then we will write down the definition of divergence f. We have considered a region of space at each and every point of which vector f is defined. In that region, we have considered a point P, and we have imagined a small volume delta V that contains the point P. The bounding surface of delta V is S, and ds is a surface element of S, at which the normal unit vector is n cap, and at which the value of the field is vector f, which is in this direction, say. We are therefore perfectly placed to define now what we mean by divergence of vector f at the point P. Let us write it down. The definition is: we can also write it in this way using the symbol. Divergence of f is a ratio of flux of vector f across delta S per unit volume as the volume shrinks to this point. This is the definition of divergence, and let us write it mathematically. Volume tends to 0, so we have to put the limit. Now we have to write down the flux, the outward flux of vector f across the surface S. Or if you want, you can write it in this way. The same thing. We have thus defined what we mean by divergence of vector f at the point P. We will now come to the physical significance of what we defined. Before going into physical significance of divergence of a vector, or explaining what it actually represents or means, let us write down the form of divergence in Cartesian coordinate system. Consider a vector A, and we can resolve it in the Cartesian coordinate system as then the divergence of vector A will be, we know what we mean by grad, del x plus y cap del y plus z cap del z dot and this is del x of ax del del y of ay, del del z of az. So this is the form of divergence in Cartesian coordinate system. We will now give an example through which we will establish what divergence A really means, or what is its physical significance. Suppose vector A is what will be divergence of this vector? We have the formula over here. So del del x of the x component, and in this case the x component is x. Del del y of y component, and in this case for vector A the y component is y. So this gives us 1 plus 1 equal to 2, and this is greater than 0 or positive. So this vector has a positive divergence. Now what do we mean by this statement? To understand that, we have to make a plot of vector A in the xy space, and we shall do that now. So let us make a plot of vector A in xy plane. So here we will put the x values, here y values, and here is vector A. Let us start with 0, 0. 0, 1, 0, minus 1, 1, 0, minus 1, 0, 1, 1, 1, minus 1, minus 1, 1, and both minus 1. This is 0, 0, so we have a 0. This one is x0, y is 1, so we'll have j hat. This is minus j hat. Here we'll have I cap, and here minus 1, so we'll have minus I cap. 1 and 1, so I cap plus j cap. 1 minus 1, so I cap minus j cap. Minus 1, 1, so it is minus I cap plus j cap. And finally both minus means minus I cap minus j cap. It is now our turn to make a plot. Let us now make a plot of vector A in the 2D xy plane. So this is the x-axis, and this is the y-axis. This is the origin where vector A is 0. So we start from here. Next we come to 0, 1, which is x0, y1, means we are here, and the value is j hat. Next is 0 minus 1, where the value is minus j hat. So we are here, and vector A is along minus j cap. At 1, 0, vector A is I hat. So x is 1, y is 0 is here, and the vector is along this direction. At minus 1, 0, vector A is minus I hat. So minus 1, 0 is here. So this is the direction of vector A. Next, at 1, 1, vector A is I cap plus j cap. So we move 1 unit along x and 1 unit along y to arrive at this point whose coordinate is 1, 1. Now this is I hat and this is j hat. So I cap plus j cap is along this direction. At 1 minus 1, where vector A is I cap minus j cap, we are here, x is 1, y is minus 1, so we are here, this is I cap and this is minus j cap, so the resultant is in this direction. So this is the direction of vector A at this point, which is 1 minus 1. At minus 1 1, minus 1 1, we are here, where vector A is minus I cap plus j cap. Minus I cap is here and j cap is along this direction. The resultant will be along this direction. And finally, minus 1 is x is minus 1, y is minus 1. We are here, where vector A is minus I cap minus j cap. So at this point, this is minus I cap and this is minus j cap. So this is the direction of vector A at this point. Now what information do we get from this plot of vector A in 2D plane? We see that at all these points vector A diverges, and the common point of divergence is the origin. At this point the vector is directed away from the origin. It is also directed away from the origin at this point, and the same is true for all the points. In other words, vector A is a divergent vector, and we have verified it through a plot and mathematically just by stating that divergence A is equal to 2, which is greater than 0 or positive. So this is the power of mathematics, where without going into a plot we can predict the nature of vector A, which we find to be divergent. Now this common point of divergence is a point from which vector A spreads out or diverges, and therefore this point is called a source point. So we can write vector A to be a source field, and the origin is the source point. It is clear that if we construct a vector, say vector B, which is equal to minus vector A, that is, it is minus of then all the directions will get reversed and we will have this type of plot. In other words, now the vector B is converging to the origin. So vector B will be a convergent field. This type of field is called sinc field. and in this case this origin is a sync point, and divergence of vector B will be the x component, the y component. So this is less than 0, so this is negative, which means that this vector B is a convergent field. Let us mention another example to highlight the physical significance of divergence of a vector. Suppose vector A is xi cap minus yj cap, and let us make a plot. Zero, 0, this gives 0, 0, 1, and this gives minus j cap, 0, minus 1, and this gives just j cap, 1, 0, for minus 1, 0, it is minus I cap. For 1, 1, we have I cap minus j cap. For 1, minus 1, it will be I cap plus j cap. For minus 1, 1, it will be minus I cap minus j cap. And for minus 1, minus 1, things will be reversed, so it will be minus I cap plus j cap. Let us now make a plot. This is x-axis, this is y-axis, this is the origin at which a is 0. Next 0, 1, so x is 0, y is 1, so we are here, and vector is minus j cap. 0, minus 1, so we are here, and vector is along j cap. At 1, 0, vector is I cap. This is 1, 0, so this is vector A, and at minus 1, 0, it is minus I cap. Next, at 1, 1, that means x is 1, y is 1, so we are here. And vector A is I cap minus j cap, so this is I cap and this is minus j cap. So vector A is along this direction. At 1, minus 1, vector A is I cap plus j cap, so x is 1, y is minus 1, so we are at this point, and this is I cap and this is j cap. So vector A is along this direction. At minus 1, 1, vector A is minus I cap minus j cap. X is minus 1, y is 1, so we are here. This is minus I cap and this is minus j cap. So vector A is along this direction at this point. At minus 1, minus 1, it is minus I cap plus j cap. X is minus 1, y is minus 1, so we are here. This is minus I cap and this is j cap. So vector A is along this direction. This is vector A in 2D plane. And what information do we get regarding vector A? Looking at this plot, this arrow shows that something is coming from up above, and then that something is not going here. Rather, it is getting scattered or spread, and therefore we have these arrows. So something is coming from up above and it just spreads or scatters. Here too, this arrow sign or these arrow signs indicate that something is coming from down below, and then they do not go to the origin, but rather they spread out here. In other words, nothing is stored at this point. Things are coming from up above or down under and getting spread out here and there. So what can we say about this point? Is this a source of something? It is not a source of something. The things that are spreading from this point is not coming from here. This arrow does not indicate anything that is coming from here. Rather, it indicates spreading of things that are coming from up above or down below. Also, things that are coming from above or below are not falling upon at this point. So it is not a sink also. So this point is neither a source nor a sink. Nothing is stored here. And this type of field is therefore called no source, no sink field or solenoidal field. So let us write these things. Vector A is called solenoidal. It is neither source nor sink. Nothing is stored. Things come and go. If we ask what is the divergence of A from this point? For divergence, something should be stored here. Since nothing is stored here, the answer will be there is no divergence. And also, since nothing is stored here, this means nothing is falling upon it, so nothing is convergent upon it. The situation is therefore like this. This is a source point. So this is spreading. And similarly, and here too there is a source. And things are spreading out from the source. So what about this point? So this is a solenoidal point. Nothing is stored here. This is neither a source nor a sink. This is a source. This is also a source. And the sink is here. The sink is there. So this is the A field. Information regarding the A field at this point can be directly obtained without any plot if we evaluate the divergence of vector A. The x component is x and the y component is minus y. So it is 1 minus 1, that is 0. So divergence A equal to 0 indicates that the field is solenoidal. With this discussion in the background, let us write down the physical significance of divergence operator.